Thank you very much. This talk will be a very introductory talk on the basic machine learning algorithms. Try to go from the very basic to the more recent and exciting one related to the current research. So machine learning is broadly subdivided in three classes. Supervised learning, where there is available a training set with some observations and the correspective ground truth. There can be labels or values that can be used for training, for optimization. Unsupervised learning, where this data set is not available. Yes, it's not available, and the machine has to learn on its own. And reinforcement learning is a third technique that has become very, very popular over the last few years, where the machine, the agent term in this case, interacts with the environment, has to learn autonomously what is the best behavior through trial and error. So a very popular and basic machine learning algorithm is the linear regression. A linear regression is just a linear model, and the true model has a linear combination of the input features or input predictors, so-called, plus some noise. And the algorithm tries to fit the model with the linear combination of the input features. And this is really, for example, if the true model is linear, then there would be a relatively easy fit, making the optimization, choosing the right parameters to fit this model. However, very often the model is not linear. Very often a linear model is not adequate, and there are techniques to improve this very basic technique, enlarging the so-called feature set, having not only the original regressor, original features, but, for example, in this case, with what is called polynomial regression, having powers of the original features that contribute to the linear combination. So this is still a model that is linear in the sense that there is a linear combination of entities, but these entities are themselves potentially linear functions of the original parameter, or the original inputs, original features. And this is important. However, this opens up a very central problem of machine learning, the one of model capacity and overfitting. So on one hand, the task is to solve a problem, not knowing exactly what is the complexity and the capacity needed to solve that problem. On the other hand, if the capacity allocated for that problem is bigger than what is needed, there is a possibility of overfitting, having a perfect training error, but then not performing well when one starts to tackle test observations, so-called test examples, so examples that have not been observed before. And this, of course, has to do also with the amount of training data that is available. For example, in this picture, there is a case where the true model is a square function. And of course, in this case, having a square approximator does a good job. And perfect fit between the true model and the assumed model by the regressor. But if, for example, one tries to fit the examples using a sixth-order polynomial in this case, then, of course, there is a perfect fit with respect to the training observations. But actually, any new test example would be grossly, would be having a gross test error, would be potentially having a very large test error, especially at the edges of the available data. And as I said, this is a very central problem in machine learning, and there is the very baseline way to approach this problem is to introduce regularization. So, of course, there are many ways of regularizing a problem. A classical way is to introduce a norm penalty to the cost. So just to clarify, in this formula, the cost, the loss function, is the quantity that the algorithm tries to minimize to optimize the weights, to optimize the parameters. And if you over-parameterize your model, you have probably too many options, too many possible solutions, actually an infinite number of solutions very often. So the goal of regularization is to reduce the scope of possible parameters that can be considered for optimization. And in this particular case, in the pictures on the right, of course, the norm penalty has the effect of reducing the norm, square norm, or L1 norm of the parameters, parameter vectors, except in the cases where the loss cost expresses a strong preferences to do otherwise. So basically, it's a smooth, soft addition of preferences to constrain the possible solution that the network implements. This is very general, also applies to the very modern deep learning, although I made the example for linear regression. It's even more interesting and important for more recent and modern architectures. Then just to go quickly through the very basic techniques. logistic regression is just the extension of linear regressions to classification. For example, in the case of a binary classifier, what this model does, it still has a linear combination of the input through a certain set of parameters, but then this linear combination is passed through a nonlinearity, a logistic function from which the name logistic regression. And the function of the nonlinearity is to produce a real number between 0 and 1, which can be interpreted as a probability. So this is a probabilistic model in a sense that derives the conditional probability of the class being 1, given the input and the parameters. And the fact that it's probabilistic implies some advantage in optimization. And so this is just exemplifying what the logistic function does. It's the stronger is the output of the linear model towards positive or negative numbers, the stronger is the highest is the probability for the class being 0 and 1. For classifiers that don't generate a probability but tries to make a decision on the class directly, then there is the problem that there are normally an infinite number of possible hyperplanes that separates classes. Assuming that two classes in this binary case of the picture can be linearly separable, even in this case, there would be more than one solution. Of course, the maximum margin classifier identifies the best solution very reasonably as the one that has the maximum margin, so the largest minimum distance with respect to the points of each individual class. And this makes sense because it makes the classifier more robust. And the additional advantage of this technique is that the points that are circled are the ones that are actually on the margin, or in this case on the margin. We'll see that sometimes it's possible to be on the wrong side of the margin as well. But these 3 points in this picture are what are called support vectors. And the advantage of this is that the hyperplane, the decision boundary, is actually determined just by these vectors, which is it's efficient because at test time, only these vectors need to be taken into the computation that is necessary to classify new vectors, new test observations. So this is expanded in the support vector classifier. In this case, there is a flexibility, so there is less possibility of overfitting again, by introducing the possibility of violating the margin. So one can have this epsilon I are what are called slack variables. So those are quantities that are allocated to points in the training set that can be on the wrong side of the margin. For example, any point that is on the wrong side of the margin has an epsilon assigned bigger than 0. And the point could even be on the wrong side of the hyperplane, in which case the epsilon is bigger than 1. And there is a constant c, which is in a hyperparameter, which allocates a budget for the total amount of violations that are admitted to a certain problem. And this margin basically sets the trade-off between overfitting and having a certain number of wrongly assigned training data. The advantage of this is exactly the similar concept of support vectors. In this case, the support vectors are also making mistakes in the classification, but there is more flexibility and less possibility of overfitting, especially in cases where the classes are not exactly linearly separable. This could at least implement an approximated solution. The best solution when the classes are not linearly separable is the support vector machine. And this intrinsically generates a nonlinear boundary, nonlinear decision boundary between the classes. And very simply, it's probably not as easy to say it in 2 words, but very simply, these algorithms exploit the kernel trick. So they identify that linear approximators, they use inner products between vectors, between the test vectors and the vectors that are part of the training observations. And substituted these inner products with inner products of functions, phi, it's as if one had made a pre-processing on the original test vectors and translated the problem from the original space to a transformed space. And what this allows, if one had done that, in the transformed space, would be possible to implement a linear classifier. For example, if it was a space that contains more dimensions, it would be possible to have the data linearly classified, even if they were not linearly classifiable in the original space. But the smart trick is that it's possible to do this with support vector machines without even leaving the original feature space. Just implementing the kernel, one even avoids to implement the inner products of the functionals phi, and just implements a linear combination of the kernels. and does the same job in the original feature space. So this was a very brief introduction of the very basic algorithms. But of course, as we've briefly discussed, many of these algorithms already identify crucial topics and issues that are really very relevant also for modern architectures. Another class of algorithms are based on Bayesian learning. And this slide sets just a very basic definition of what is a biased net. A biased net is a set of variables. These are the nodes in this graph. It's a directed graphical model with some nodes and some connections. And the edges are important because they define the conditional dependence between nodes, the conditional dependence between variables. So the presence of a node, or of an edge between two nodes, means that, for example, node x2 is conditionally dependent on x1. At the same time, the absence of a link between x3 and x2 means that x3 is conditionally independent of x2 given x1. And this is applied by the naive Bayes classifier, which is naive Bayes. It's called naive because it makes a very strong assumption on conditional independence. It's so strong that it's not always applicable, but it's so crucial into make it possible to have an efficient implementation of this class of algorithms that become very popular. It's a very popular baseline classifier, for example, for text categorization, for document classification, and in its simplicity, its efficient calculations are its strength. Of course, the performance depends on how the assumption made is acceptable in the particular problem that one faces. So what does this imply? So on the figure, in the graph on the right-hand side, there are the input variables, the input features of a d-dimensional input space that are all conditionally independent from each other, based on the assumption of the naive Bayes classifier. They're all dependent on the class. So the other aspect worth mentioning is that this classification compared to logistic regression, instead of computing the probability of the class given the input, computes the probability of the input given the class. What is in red, P of x given y. Now, the problem with this is that if one has a d-dimensional vector in the input features, the vector x, so the string of elements x1 to xd, can, if these are binary elements, has 2 to the power d possible values that can be implemented. So the number of parameters needed for this model is proportional to an exponential number in the dimension of the input space. However, making the conditional dependent assumption, this joint probability of the input variables conditioned to the class can be made into the product of the individual probability of each input variable given the class. And of course, in this case, the number of parameters needed for the model is only linear in the number of input dimensions. And why is this important? I mean, the number of parameters is directly related to the number of test examples that are needed to train this network. So having a dramatically reduced number of examples makes it possible for this network to produce good results even if the data set is not very big, which is the strength of the algorithm. Really, on the opposite side, k-nearest neighbor, it's again a very popular and traditional machine learning algorithm. It's a classifier, can be used as a regression as well, but as a classifier, it's very simple to explain. For a new test observation x, what it does, identifies the k, where k is an integer, positive integer, identifies the k closest training points that belong to a set, the set of the k closest training point to the new observation. And then out of these k points, finds the class that is represented most, that has the largest number of members within this set. And that's the class that is chosen for the classification. So it's a very simple classifier. The problem is, there are two basic problems. One is very costly, because for any new element to be classified, one has to compute the distances with respect to all the points of the training set. And the other problem is that doesn't perform well for high-dimensional inputs. Is the input dimension, number of dimensions of the input is high, of course it's more and more difficult to find enough points to do a good job in classifying. And so it's the opposite of the naive Bayes, although it doesn't make any assumptions, very general, but then can be very problematic when the number of dimensions are very big. Then there are some very simple algorithms that are trying to put the structure in the original data set. For example, k-means clustering identifies a way to cluster the points of the original data set. So one identifies k initial centers for the clusters, and then iterates the following procedure. The first aspect of the procedure is to allocate to each cluster the closest point, and then to recompute the cluster mean, the cluster center, from which the name k means. So every time there is a recomputation of the mean for all the k clusters. Differently from clustering, so clustering that we have just seen tries to determine the structure into building subgroups of the original data. Principal component analysis instead tries to learn a lower dimensional representation of the data, and thus this is obtained by analytically finding the eigenvector of the covariance matrix. But more intuitively, what principal component analysis does find the directions of the space where there is most variance, tries to justify the variance, the variability in the data. So identifies at first the direction of the most variance, and then the direction where there is most variance about the remaining dimensions as conditioned to being orthogonal to the original dimension. Those are the principal components. And this procedure eventually identifies an orthogonal basis that justifies the variations in the original data set. So contains the structure of the original data set. Now, I mean, I'll probably slow down on decision trees because it's slightly less old technique, although they're not, they were really fashionable before the advent of deep network. They were the best performing, especially ensemble of these trees, like we will see. They were the best performing machine learning algorithms for many competitions, but with the advent of deep network, there have been other architectures that are nowadays even more popular. But what the decision trees do, they try to break the original feature space into regions, boxes. They're really high-dimensional rectangles. And this can be done for both classification and regression. For classification, in each of these boxes, the class that is allocated, if a new example ends in that box, the class that is allocated is the one that is most common in that box. So the way the tree is grown, in that case, is in order to have as much purity, as much as possible element of each individual class in each block. So the tree is grown and the space is broken up, split by split, in order to group individual classes, element of each individual class on their own. In case of regression, the mechanism is slightly different. In case of regression, the mechanism is reduce at each split, try to reduce the residual sum of square cost. So for each of the boxes, a new element, a new observation, test observation in that box gets given a value which is the average of the value of all the training example for that block, right? So it's really an approximation of a function, a stepwise approximation of the function. And of course, the smaller the error in between the average of the points that belong to one region and the individual elements that belong to the region, the lower is the residual sum of squares. So that's really the mechanism by which the tree is grown. But as I just mentioned before, trees has the advantage of being interpretable. Visualization is another strong point of trees, but the performance of trees on their own is not always best in class. It's improved, however, dramatically by using ensemble of trees. So the first class of ensembles of trees is with bugging. Bugging stands for bootstrap aggregating. It's a technique where many trees are grown in parallel using the technique called bootstrap. Basically, we have one data set, and what bootstrap does, bootstrap allows to generate multiple subsets of data from the original data set through drawing randomly data with replacement. So there is the original data set, one draws data, this constitutes a new subset of data, and that is used to grow one tree. And the process is repeated several times until one is able to grow independently a certain number of trees, and at the end, For example, for regression, one computes the average of the predictions made by these individual trees, and the performance and robustness of this algorithm is dramatically improved. There are other ways of doing this, however, and random forest is even better performing than boosting. And random forest identifies that using the bootstrap, there is still a correlation left among the subsets of data that has been obtained from the original data set. However, a way that random forest exploits to reduce this correlation is to use only subset of predictors, subset of features for each split of each individual tree. So in each individual tree that is grown from its own subset, every time that there is a split, not all the predictors, not all the dimensions of the original input features are used. So this introduces a variability, especially introduces the possibility of disregarding some very strong predictors, and this variability reduces the variance because there is less correlation, and of course the variance is reduced automatically, and automatically the test error is improved. To conclude, again, in terms of ensembles of trees, boosting is a family that is similar in concept to bugging and random forest, but actually the weak learners are combined not in parallel but in sequence. So what boosting does, uses a data set, but instead of using the bootstrap technique, bootstrap resampling, uses a data set to grow one tree, and then, depending on how the tree has performed on the examples of the training, modifies weights differently the original data set, emphasizing the example that have not been, where the previous trees have not been performing well. So increasing the weight of, for example, in case of classification, increasing the weight of examples that have been wrongly classified, or in case of regression, increasing the weight of example where the regression error has been higher. So those were, as I said, very popular until not many years ago, but nowadays the most popular architecture are really based on neural networks and deep architectures. And the broader classification of neural networks are feed-forward neural networks, convolution neural networks, and recurrent ones. Convolutional have been achieving over the years outstanding results in image processing applications, face recognition, sign detection, pedestrian detection. And as we will see briefly, they have a very strong prior towards image processing. They are very efficient in computation that are common in case of image processing. Recurrent neural networks are instead very popular, have achieved outstanding results in when the input is a sequence, for example, speech or text. So in general, in natural language processing applications. Before going to convolutional networks and recurrent networks, the very basic feed-forward network architecture, deep network architecture, I'm emphasizing the depth aspect of it. It's a stack of multiple layers, in this case, for a feed-forward network, a stack of feed-forward layers. And the strength of the deep architecture is the possibility of reusing features and representation that have been built bottom-up from the first layer, parameters, and their features, their work is reused by the layers above in turn. And this reuse of features and representation makes very efficient the calculations that are implemented in this network. So the network itself it's really a mapping, a nonlinear mapping. Each of these feed-forward layer blocks contains a fully connected layer and nonlinearities, which we'll get more into the detail in 1 second. But basically, this nonlinear mapping, for example, for classification, after the series of layers is followed by a softmax layer, which produces a probability of a class. So at the end, the entire feed-forward network can be seen as a conditional probability estimator for a certain class given the input. And then the output of the softmax layer is used to compute the loss. And then the problem of how to learn the parameters of all the layers is through backpropagation, typically. So basically, after having obtained the output of the last layer, the backpropagation computes the gradient of the loss with respect to the output of the last layer, and then this gradient is backpropagated using the chain rule of calculus. So each layer during this backpropagation receives the gradient of the loss with respect to its output and uses that parameter to derive the gradient of the loss with respect to the parameters, the weights of that particular layer. And then update the weights, and then progresses computes the gradient of the loss with respect to its input, which is again passed to the previous layer and so on. So I'm saying this because it's really one of the crucial aspects of deep networks. Is what for this so efficient network still implies some computation to be done in learning that is the subject of lively debates over the last few years. But going back to the feed-forward neural network architecture, each layer, it's a linear layer, and is made of units which have some link into the biological neurons. Basically, each one of these units have connections to the units of the previous layer, and each one unit has its own activation function. So after this fully connected series of connections, each one of these units has a function which in modern deep network is typically a rectified linear unit function. And then the formalism is an affine transformation, really a linear transformation for the connection between units of one layer and the one of the next layer, and the nonlinear activation functions produces the final output of the layer. So this is for the basic feed-forward networks. Then the convolutional networks inherit all the advantage of the deep architecture that we have just described. On top of it, there is the convolution that is the strength in terms of image processing of this architecture. So each convolutional layer has a convolution operation followed by nonlinearity, followed by pooling. And what the convolution does, computes for each of the input maps, what are called input feature maps. For the first layer of the stack, those are the input images. And then going towards the output of the architecture, those are more and more abstract representation of the features that the network builds and are called input features. But the way those are processed is always the same from the first layer to the last layer. There is a kernel, there is a series of parameters that have a certain height and width, and that these parameters compute a local weighted average of the particular set of information they find on that particular input feature map. And then they scan, they slide over the input feature map, and the same parameters are used within one feature map. The reuse of the parameters, the use of shared parameters, is important because it reduces the overall number of parameters that are employed by these networks, which make the architecture efficient. And of course, after each of these operations, there is a nonlinearity, a rectified linear unit, like in the feed-forward networks, and then a pooling layer, which typically max pooling in convolutional neural networks. And what this pooling does, out of a certain region, a certain field at the input of the pooling layer, for example, if it's a max pooling, detects the highest intensity of this field, and that's what is passed to the next layer. And it typically is associated to a reduction of dimensionality to the next layer. And it's really tries to merge the similar features among the different input features going through the architecture. So probably there are many more architectures that might be worth discussing than just one, but having to choose one, the ResNet architecture is one of the most popular convolutional network architecture being used over the last few years. So it's a convolutional architecture. The difference is that in each one of these called residual block, there is a shortcut connection. And the shortcut connection is important. Initially, the importance has been attributed to the fact that in backpropagation, the gradient can flow unimpeded through these shortcuts. But actually, even more compelling interpretation is based on the fact that all these shortcuts that are present in each individual block create multiple paths. So it's as the architecture was an ensemble of many networks of different depths. And of course, being an ensemble, we know from trees that the diversity that ensemble produce improves the performance. And in fact, these are among the best performing architecture. So the convolutional networks reuse the weights over the spatial dimension, over height and width of each feature map. Recurrent neural network, they reuse the weights in a different dimension. So what they do, they have an input that go to a hidden layer. This is just one unit of a typical recurrent neural network. The hidden layer H, and then from the hidden layer, they have another linear transformation that produces an output through a transformation V. So there is also, very characteristically, a self-connection with parameters W. So each hidden layer at one point during the sequence is also connected to the same layer at the next stage during the sequence. So in the unfolded representation, we have the X represent the different elements that are presented at the input of this network when the input is a sequence. So each one of these xt minus 1, xt plus 1, they're not necessarily different time instances, but they're different elements of the sequence that is produced at the input of the network. And this is clarifies the operations that are implemented over the sequence of inputs. And basically what happens is that there is a processing done to maintain information over whatever has been seen by the network through the input sequence in the hidden layer H. And this is done reusing the same set of parameters W. So the fact of reusing the same parameters over the input sequence dimension makes it efficient again, reduce the overall number of parameters, and makes it efficient in the sense not only requires less calculations in terms of training less parameters, but also require less training data to train the parameters, which is crucial. So this is just the operation, just the operation for the operation that, for the steps as just described. What is to be emphasized is that the nonlinearity in this case is more often a hyperbolic tangle on a nonlinearity that has saturations to help stabilize the backpropagation through time. And finally, in terms of recurrent neural network architecture, there are situations where one can have a feed-forward path and a backward path. So when accumulating information from the past to the future and from the future to the past. Of course, this implies that one has the entire sequence available for processing. And the advantage of these solutions is to have a more flexible implementation than just a fixed look ahead. Then LSTM cells are just one example of a very popular RNN, recurrent neural network model. So the main advantage of LSTM are not new, are not recent. They have been invented in 1997. It's amazing how amazing results they have produced even over the last few years. They have been really the core of best-in-class performance in terms of handwritten recognition, handwritten generation, speech recognition, image captioning, which is a very exciting recent development. And basically, the winning technical element has been that is in LSTM cells is an internal state C, which is not that dissimilar to an exponentially weighted average of the accumulated information inside the memory cell. So there is a parameter, this multiplier here, it's a weight that could be interpreted as the parameter of the exponentially weighted filter. The difference is that this weight is actually dynamically modified by a forget gate. So this weight is dynamically modified by the forget gate depending on the input state and the input signal and the state at the previous step of the network. So it's the time constant of the integration are dynamically changed, which makes it possible to accumulate information in the memory cell, but also forget information that's no more relevant for the task. And all the architecture, it looks quite complicated. This also has what is called an input gate and an output gate. There are other architectures that are not that different in terms of performance, the so-called GRU, gated recurrent units, that have only 2 gates instead of 3, so they're slightly simpler, but the performance is not too dissimilar. LSTM is still often superior in performance. So after having seen neural networks, different types of neural networks, just to conclude, I thought it was relevant to just briefly mention reinforcement learning. This is it's one of the most popular recent development of machine learning, and broadly speaking, it's very different in terms of concept with respect to even both unsupervised and supervised learning. Even compared to supervised learning, there is not a ground truth. The agent has to perform actions, access the environment by trial and error, performing action, and observing the state of the environment, and potentially seeing some reward, and using the state and reward to learn how to change his own policy to improve his behavior and his interaction with the environment. Deep reinforcement learning, the more recent implementation of these techniques, they're called deep reinforcement learning because they use deep neural networks as function approximators to implement either only the policy or only the value function or both, like in this case. So there is a policy which is a neural network, and this neural network is held by the value function network. Basically what they do, the policy network is the one responsible for deciding what action needs to be taken, and the value function network is the one that estimates the expected rewards. So computes function that makes it possible to update the weights of its network and also to the policy network. Overall, therefore, this reinforcement learning implementation reusing function approximator as like the neural networks, maximizing the expected reward, reusing the type of signal processing, the type of machine learning algorithms that we have seen before. So basically, both the policy network and the value function network, or one of the two, it can be a convolution network, can be a recurrent neural network. So both of them are trained through backpropagation, which is potentially also a problem. And the other aspect that is worth mentioning is that the policy that is learned through this interaction with the environment on its own is not enough to make sure that the optimal reward is always, the goal of the maximization of the expected reward is reached. What I mean is that there is the need for exploration because there is not a ground truth. So the main differentiation with respect to supervised learning is that the network needs also to explore. And the exploration in this case, in the case of traditional reinforcement learning, is done by trial and error on the actions. So the policy decision of implementing an action is stochastic because there is the necessity of allocating some of the actions towards exploration instead of exploitation, instead of getting rewards. And from that point of view, it's worth mentioning that there have been recent discussions on alternative approaches, completely different approaches to the same problem. And one exciting new discussion is related to evolution strategies. Again, in this case, the goal is to maximize the expected reward. But now, the policy, it's just a black box optimization that doesn't use backpropagation, which is one of the reasons why it has been debated. Not using backpropagation, this approach can be potentially faster. And the black box optimization is based just on finite difference estimation, allegedly only a subset of direction at the time. And the other aspect that is worth mentioning is that in this case, the exploration is done on trial and error on parameters. So it's a direct policy optimization where the parameters have some stochasticity, which is what helps in exploration. So I think I probably just left enough time for some question and answer. Thank you very much.